So let's look at a formal algorithm to explore a graph. So recall that a graph consists of a set of vertices and a set of edges. The edges are the connections between the vertices. They may be directed or undirected. So if you look at an undirected graph, the problem we are looking at is to find out whether a source vertex is connected to a target vertex. And we said that this amounts to finding a path from V0, the source vertex, to Vk, the target vertex, where each pair of vertices on the path is connected by an edge in the graph. So we argued that we could easily do this for small graphs visually, but if we want to write an algorithm, we need a way of representing the graph. So the first thing we decided was that we would name the vertices 1 to n. So if we have n vertices, we will just call them 1, 2, 3, 4 up to n. Then we can represent the structure of the graph through an adjacency matrix. In this adjacency matrix, the ijth entry indicates the presence or absence of an edge from vertex I to vertex j. So aij is 1 if there is an edge, aij is 0 if there is no such edge. In this matrix, if we want to find out whether a pair of vertices are directly connected, we just have to probe the appropriate entry. So we can do that in constant time. To find all the outgoing neighbors of a vertex, we have to scan the row for that vertex. So that takes linear time in terms of the number of vertices. Now one thing we observed is that typically in many graphs, this matrix is largely 0. Most pairs are not connected. So we can get a more compact representation by just listing out the neighbors of each vertex. So instead of keeping a row of ones and zeros, we just record those vertices whose entries are 1. So this gives us a more efficient representation for graphs where the number of edges is closer to the number of vertices. But in this case, in order to find out whether a given pair ij is connected, we have to look at the list for I and see if j appears in it. Now our strategy for finding a path connecting a source vertex and a target vertex was as follows. We would start at the source vertex and keep exploring the graph systematically. Each time we went to a vertex, we would mark it as visited. And then we had to make sure that when we were exploring vertices, we did not re-explore the same vertex twice. So we said there would be two fundamental strategies, breadth first and depth first. So today we are going to look at breadth first search. So the idea of breadth first search is to explore the graph level by level. So we start at the source vertex and we now explore all the vertices which are one step away, connected by a direct edge to the source vertex. Then we look at all vertices which are newly connected one step away from level 1 vertices. So these are 2 steps away from the source vertex. And then for 3 steps and so on. Now while we are doing this exploration, we have to keep track of 2 quantities. We have to first note, of course, whether a given vertex has been visited. Has it been explored? Is it connected to the source vertex? Also for each such vertex, we have to explore its neighbors. Right? So for each vertex, we need to know A, has it been visited? And we may not be able to explore it as soon as it is visited. So we need to remember that we have explored it or not explored it. And those which are not explored, we have to make sure we explore them once. So the way to do this is to use some data structures to keep track of these quantities. As we said, the set of vertices is numbered 1 to n. So we can keep an array visited with entries 1 to n, which tells us whether or not vertex I has been visited. Now, whenever we visit a vertex, we need to subsequently explore it. Since we may not explore it immediately, we may have to keep it pending for a while. So we have to keep a collection of these vertices which have been visited but which have not yet been explored. There are many ways to do this, but one natural way is to explore them in the order in which they were visited. So if you want to explore in the order in which they were visited, a natural data structure to keep the list of unexplored but visited vertices is a queue. So we put each visited vertex into the queue the first time we come to it, and then we process all the vertices in the queue until all vertices have been explored. So here is some high-level pseudocode for breadth first search. When we reach a vertex I, which we have visited for the first time, we will eventually explore it. What does it mean to explore a vertex? We look at the outgoing edges I, j. If j has already been visited, we have nothing to do. On the other hand, if j has not been visited, then we will mark it as visited and add it to the queue to be explored later. So we begin by marking the source vertex and adding it to the queue. And at each stage, we will explore the vertex at the head of the queue. If at some stage there are no vertices in the queue, it means that every vertex we have visited has been explored, and so there is no new information left and we can stop the exploration. So before giving the actual code for breadth first search, let's work out the example that we have and see how these data structures are updated. So we have these 10 vertices 1 to 10, and we are looking for paths starting at 1. So in the queue, we have two pointers as usual. We have a pointer which we indicate in green, which is the head of the queue, and a pointer red, which is the tail of the queue. So we initialize the queue to have the starting vertex 1, and we also mark this vertex as being visited. Now we have to explore 1. So what we do is we remove 1 from the queue and systematically check each of its outgoing edges, and if those target vertices are not already visited, we add them. So 2 is the first in order of 1 to 10, first neighbor of 1. It has not been visited, so we add it to the queue and mark 2 as visited in the visited array. Likewise, we mark 3 as visited, and then we mark 4 as visited. At this stage, we have finished exploring vertex 1. So now we go back to the queue and see if there is anything yet to be explored which has been visited, and there is. So we pick up the first such, namely 2. So we remove 2 from the queue and we explore its outgoing neighbors. Now the outgoing neighbors of 2 in this case are 1 and 3. But since 1 and 3 are both visited, we have no work to do, and we go on and go back to the queue. So in the next stage, we pick up the vertex 3 and we look at its outgoing neighbors. Again, it has outgoing neighbors 1 and 2, both of which are already visited, so there is nothing to be done. We come back to the queue and pick up 4 and try to explore it. So 4 has a neighbor 1 which has already been visited. The next neighbor is 5. Since 5 is new, we add it to the queue and we mark it as visited. And then it has a neighbor 8. So we add that also to the queue and mark it as visited. Now we have finished exploring 4. So we go back to the queue and look for the next thing to be explored, which in this case is 5. So 5 has got neighbors 4, 6 and 7. 4 has already been visited, but 6 is new, and so is 7. Now we go back and explore 8. So 8 has neighbors 4, 6 and 9. 4 and 6 are old, but 9 is new, so we add 9 to the queue. Now we go back and explore 6 because 6 is the vertex at the head of the queue. So now we look at neighbors of 6. The neighbors of 6 are 5, 7, 8 and 9. So when we remove 6 from the queue, we have nothing to do. We go back and find that there's nothing to be done because all the neighbors of 6 have already been visited. Then we pick up 7. Once again, we find that all the neighbors of 7 have already been visited. Finally, we pick up 9. When we pick up 9, we find that it has neighbors 6, 8 and 10. 10 is new, so 10 gets marked and added to the queue. Finally, we go to 10 and we find it has only one neighbor 9 which is already visited. At this stage, the queue becomes empty and the algorithm terminates. Now in this case, we have marked all the vertices as visited, which indicates that every vertex in this graph is actually reachable from 1. If we had had more vertices, for example, if we had had a component in this graph, there is nothing to stop us from having many components, so we could have had a graph with more vertices 11, 12, 13 and 14, then this process starting from 1 would have left 11, 12, 13 and 14 marked as unvisited. So here is some more formal code for BFS. So BFS is a function which takes as its argument the vertex from where we want to explore the graph. So as we said, the vertices are called 1 to n. We have this array visited, which is initialized to 0, and we have a queue to mark the vertices still to be explored, and this is initialized to empty. So we begin by marking visited of I equal to 1, so vertex I is marked as visited, and we add it to the queue. Now, so long as the queue is not empty, we proceed in the following loop. We extract the head of the queue, the vertex to be explored next, for each of its outgoing edges. If it is something which has not been visited before, we mark it as visited and we add it to the queue. Right? So this is exactly the code for the algorithm we just executed by hand, and it's quite straightforward. There are two data structures, an array to keep track of the visited vertices and a queue to keep track of vertices which need to be explored further. So how do we analyze the complexity of an algorithm such as this? One way to do it is to look at the loop. So remember that when we have an algorithm like this which has a loop, the loop is usually the place where we have to look for it. So we have one iteration where we have a loop of 1 to n where we assign visited j equal to 0. So this is something which takes order n time, right? And now we have a loop here where we keep extracting things from the queue and we do things here, right? So we have to kind of understand how many times this loop is going to execute and how much time this inner loop is going to execute. So each vertex enters the queue exactly once. Okay? So if we enter it exactly once, then it says that this outer loop here will take order n time, because assuming that the graph is connected, every vertex will be visited once, and when that vertex is visited, it will enter the queue and it will come out from the head of the queue exactly once. Now, for each vertex, we have to scan all its neighbors. So what we said was that this will be order n if we have an adjacency matrix, because we need to go from the big first entry for j and we have to look at the entire row for j. So this is order n. So therefore, if the graph is connected, first of all, every vertex will get into the queue. So we will do the queue loop exactly n times. And for each j that is extracted, we need to examine all its neighbors. So that will be a scan of size n. And therefore, overall, it's order n squared. Right? These two nested loops of size n. So this is clearly a situation where if we have very few edges, we can improve the complexity by using an adjacency list representation instead of an adjacency matrix representation. So if the number of edges is m, and m is much smaller than n squared, right? So if m is say proportional to n itself, then what we can do is in the list associated with j, we just have to look at the neighbors of j. We don't have to look at all the vertices, all of order n entries in the adjacency matrix. This is called the degree. So the degree of a vertex is the number of vertices connected to it. Right? So if we do this, then what we will find is that inside the iteration of the inner loop, each step of scanning for the neighbors takes time proportional to degree of j. Now, the degree of j, of course, varies from one node to another. So how do we count this correctly? So if you don't count it per loop, but count it across the entire processing of the entire set of vertices, what we will see is that for every edge in the graph of the form I comma j, there will be a time when I is processed and I will see j in its list, right? And there will be a time when j is processed and I will see I in its list. In other words, if I take all the adjacency lists of all the vertices, each edge will be represented twice. An edge ij will appear as an entry j in the list for I and an entry I in the list for j. So while it is not easy to count per iteration, if I count across all iterations, I will explore each edge exactly twice. So 2m is order m. So overall, exploring the neighbors across all n iteration takes times om. So what this means is that the first iteration of marking everything visited takes time on. Then we have an on loop across which we do om steps totally across the n steps. So it is overall n plus n. Okay, so the complexity of breadth first search, if we are using an adjacency list, it drops to on plus m versus order n square for the adjacency matrix. So if we have fewer edges, then it makes a lot of sense to use adjacency list for breadth first search. Now, in graphs, the input size is typically taken to be m and n. In other words, both parameters are somewhat independent of each other, because we could have a set of vertices with very few edges with very many edges. So usually m and n together are taken to be the input size. So order m plus n is actually a linear algorithm. So this is best possible because you have to read the input in order to process it typically. So in linear time, we are able to do breadth first search. So we can do something more in breadth first search. All we have identified is which vertices are connected to the initial vertex 1, or the source vertex in general from where you start breadth first search. So how do we actually identify how to go from the source vertex to a given vertex? Okay. So if we start at I and BFS I set visited j equal to 1, we know that I and j are connected, but we don't know the path. So what we can easily do is to remember where we marked each vertex from. So when we mark a vertex k as visited, it is marked because it is the neighbor of some already visited neighbor j. So then we can say that k was marked by j. We will use the word parent. So we will say that the parent of k is j. Then by following the parent links, we can reconstruct a path backwards from k to the original source vertex. So this is very easy to do in our code. So we just have to add one line, okay? So or two lines. So initially we say that for every vertex the parent is undefined. So we might set a value like -1 because we know that the names of vertices are 1 to n. Okay? And then when we mark a vertex, since we are exploring an edge jk, the parent of k is going to be j. So we assign the parent of k equal to j. The rest of the code is identical to the earlier breadth-first search. We have just added this new array parent to keep track of how we mark the vertices so that we can reconstruct the path. So we can go backwards. So because k was marked by j, j would be marked by some other thing and so on. So by just following these links back, we can go back from any k to the start vertex, and therefore we can reconstruct the path. The other thing that we can do in breadth-first search is keep track of the level. So remember we said that breadth-first search actually explores a graph level by level. It looks at all the vertices which are one step away from the source. Then those vertices are one step away from these ones. So they are at level 2, 2 steps away from the source and so on. So instead of just saying that a vertex is visited, we can ask at what level it was visited. Okay? So initially we say that all the levels are undefined, and then each time we visit a new vertex, it is one level more than the vertex from which it was visited. So eventually we say that if level j is assigned some number p, it must be p steps away from the original vertex. So this can also be easily added to our code along with the parent code. So last time we added this assignment for the parent. Now we also add the assignment for level. So we say initially the level of each vertex is undefined. So it is some nonsensical value like -1, right? Then we say that the level of the start vertex is 0. And now whenever we visit a new vertex, if it is visited, then it must have a level. So if its level is -1, right? So if its level is -1, it means it's not visited. So level -1 means not visited. This is the same as in our earlier thing, same as visited k is 0. And if so, we adjust the level of k to be 1 more than the level of j from which it was visited. And of course, we set the parent as before. So we can see how this works on our earlier example. So as usual, we start with 1 and we mark its level as 0 and it doesn't have a parent. Now when we add 2, 3 and 4, all of them will be at level 1 and all of them will have as parent 1 because they were explored from 1. Then as before, 2 doesn't add anything new to our list. 3 doesn't add anything new to our list. Now 4 will add 5 and 8. So for these two, the level will be 2 and the parent will be 4, indicating that I got to 5 and 8 from 4 in my exploration. Okay? Then from 5, I will get 6 and 7. So these are now at level 3 because 5 was itself at level 2 and therefore 6 and 7 are at level 3 and their parents are 5. From 8, I will go to 9. So 9 is also at level 3 because 8 was already at level 2. So 9 is at level 3 and its parent is 8. And finally, we will find that 10 is at level 4 and its parent is 9. So now we can trace back. So we can say that I got from 10, I came from 9. So 9 came from 8. So 8 came from 4. 4 came from 1. So the path is actually 10 to 9 to 8 to 4 to 1. And you can see indeed we have a path from 10 to 9 to 8 to 4 to 1. Right? So this is how you can reconstruct the path information and also the distance information at the same time when you are computing breadth-first search. So breadth first search, if we add this level predicate, it actually gives us the shortest path to each node in terms of the number of edges. Now, in general, we will see that if we don't have a uniform cost, if we have different costs on edges, then the shortest path need not be just the shortest in terms of number of edges. We have to add the cost associated with each path. These are called weighted graphs. But in an unweighted graph, that is a graph which just has simple edges the way we have it now, breadth first search has the added advantage of computing the shortest path in terms of number of edges from the source vertex to every reachable vertex from it.